Today we're just going to solve some trigonometric equations. The first one I have is tangent x equals -4. I'm going to use the unit circle here. So just draw a unit circle just as a sketch to help you visualize the solutions. I'm going to think about tangent x as the slope of my terminal arm. So where might the slope of my terminal arm be -4? Perhaps here and the other direction. So those are my two possible arms. I will just say that since this is tangent x and we're looking for a general solution, I only need to find one of these and then I can just add multiples of pi. We'll get to that later. But first, we need to figure out what each of those angles would be. What angles would get us to each of these arms. So I'm going to draw a reference triangle. It happens to be the same reference triangle. And I'll call the angle alpha. So if this is 4 and this is 1, because the slope is -4, I can see that alpha, our reference angle, well, tangent alpha is opposite over adjacent, 4 over 1, or just 4. And that means alpha should be inverse tangent of 4. Well, I guess that helps us a little bit, but we want to undo this tangent here. So we still need to figure out what angles from the positive x-axis get us to each of these arms. Well, if we go pi, we've overshot, but if we go pi and then we go back alpha, we're going to get exactly to that arm. So one solution for the argument of the tangent function would be pi minus alpha, and I'll write inverse tangent 4, just alpha. Another possibility is, well, what if I go 3 pi over 2, nope, not quite there. What if I go pi, nope. What about 2 pi, and then I back up in alpha as well. So another solution might be 2 pi minus alpha, the reference angle, inverse tangent 4. But note, this is the general solution, so in fact, I'm just going to add some number of multiples of pi, integer multiples of pi, in order to get all of the solutions. Because think about it this way. What if I went all the way around, I went another pi around? I'd get to another arm that satisfies tangent x equals -4. So, in general, I would say x is equal to pi minus inverse tangent 4, and then plus pi n, 2 pi minus inverse tangent 4 plus pi n, and here n is an integer. But if we want to get really technical, you can simplify this. To show you, you don't need to do it, but technically, all of these solutions are included here because these two angles just differ by pi. We'll look at this later in another problem with tangent, but because the period of the tangent function is pi. But anyway, you could say that the general solution is just inverse tangent of 4 plus pi n, or n pi. We're going to look at another example now. Sine and cosine are a lot easier to visualize. You'll see why. So, question 2, 3 sine 2x is equal to 1. Well, what I'm going to first do is try to isolate sine, the sine function, or rather the sine function evaluated at some point, because then I can undo the sine function like I undid the tangent function in the other, in question 1. So, it's like solving a linear equation in this case. We will divide by 3 on both sides, and we'll have sine 2x is equal to 1/3. Now what do? Just remember again, this is a general problem. We don't have any restrictions on x. So, I will again draw a unit circle. Just to visualize it, it doesn't have to be perfect. It obviously isn't. But I'm going to think about sine as the y-coordinate. So I might say y is equal to sine something and equal to 1/3. Well, where's the y-coordinate equal to 1/3? Maybe around here, and maybe that on the other side as well, right? So our possible arms would be here in the first quadrant and here in the second quadrant. Now, we're going to use the same idea with the reference angle. Maybe you see the angles already, but this is a bit more systematic. So 1/3 means that this would be 1/3, and this would be 1, or this would be 1/3 and this would be 1, because it's the unit circle and we want to see where the y-coordinate is 1/3. So in order to find alpha, we know sine alpha, just looking at the side lengths of our reference triangle, is going to be, well, 1/3. 1/3 over 1, just 1/3. So our reference angle just has to be inverse sine of 1/3. And we're going to do the same thing we did last time in order to figure out what the argument was. So in this case, we look at the inside, kind of just undoing the sign. 2x is the inside that we're solving for at this moment. It's just going to be, how can we get to either one of these arms? What angle will get us there? Well, what if I just go in alpha from the positive x axis in the counterclockwise direction? If I go in alpha, I have indeed gotten there, and alpha is inverse sine 1/3. How else can I get there? I could go pi, I've overshot, but if I subtract the reference angle alpha, I'm back to, an arm. So another solution is pi minus alpha, pi minus inverse sine 1/3. But it's a general solution, so in fact, to each of these solutions, we're going to add some number of 2 pi's. This is because the period of the sine function is 2 pi, or just looking at the unit circle. If I got here, if I go another full revolution around, you'll notice I have what we call a coincident angle, because it gives us the same terminal arm. Maybe I go another 2 pi around, same idea. Always the same arm, or perhaps the arm in the second quadrant. I've gotten here, I go a full 2 pi around, I've made it. I go another 2 pi around, I still made it to the same arm. So, looking at each of these, we will add 2n pi, and the other one, pi minus inverse sine 1/3 plus 2n pi, and n is an integer. If you really want to be technical about it, you'd write down n is an integer. So to finish up, we're just going to divide by 2, and don't forget to divide everything by 2. You might look at it as 2 different equations. 2x is either equal to, well, this solution set or equal to the other solution set. The idea is you solve for x, you divide both sides by 2. So you have 1/2 inverse sine 1/3 plus n pi. And then dividing this, we have pi over 2 minus, 1/2 inverse sine of 1/3, and then plus n pi. That's our general solution. I'm going to move on to question 3, which is going to involve the cosine function, one that we haven't seen yet. So cosine 1/2 x plus 1 equals square root 3 over 2. And you might instantly recognize the square root 3 over 2, but in fact, I'm still going to use the unit circle to be not only systematic, but it's going to make sure you don't miss any angles. Because you might know, well, I remember my special triangles. I know that cosine of pi over 6 gets me square root 3 over 2, but in fact, that's not the only solution. So here, I'm just going to look at cosine as the x-coordinate. So x is equal to, and this will get a little confusing because the actual equation also uses x. So I'm just going to underline, to show that it's not really x, I'm saying I want to find points where the x-coordinate is going to be square root 3 over 2. So, ignoring that, where's the x-coordinate equal to square root 3 over 2? Perhaps around here in the first quadrant and around here in the fourth quadrant. I'll start breezing through it in a little bit. But to show you all of the work, these are our 2 triangles. These are our 2 arms. So, our reference angle, note that the reference triangles are actually the same, so you only really need to draw one. Gives us this. The x-coordinate is going to be square root 3 over 2, and the y-coordinate actually doesn't matter. But we do know the hypotenuse is 1. So, if the x-coordinate is square root 3 over 2, cosine of alpha, this length here is square root 3 over 2, cosine alpha is going to be square root 3 over 2, and the reference angle alpha is just going to be, well, how do we get here? This is a special angle. You could use the inverse cosine function, but it's nice to just remember that alpha will be pi over 6. So what do we do now? Of course, we need to figure out our general solution. So how do I get to the first arm? How do I get to the second arm? And then I'm going to add multiples of 2 pi. So to get to the first arm, I could just go in alpha, which is pi over 6. To get to the second arm, I could go, well, 2 pi is almost there, but I've overshot. So it's going to be 2 pi minus alpha. So our other solution is 2 pi minus pi over 6. And don't forget, you need to add your multiples of 2 pi. So plus 2n pi, plus 2n pi. And I made a small mistake here. In fact, we were looking for the argument. This is a common mistake. I made it right now. So we were actually solving for the argument 1/2 x plus 1 is equal to one of these angles. Why does that make sense? Because you plug in pi over 6 to cosine function, which will give you square root 3 over 2. So that means the inside here must be pi over 6 or some multiple of it, or the other one, 2 pi minus pi over 6 plus some multiples of 2 pi. We have to isolate for x again. So I'm going to skip some steps, but the idea is the same. I'm going to have 2, negative 2, plus pi over 3 plus 4n pi. And then on the other side, I'm going to have negative 2 plus 4 pi minus pi over 3 plus 4n pi, if I have not done anything wrong. So, next problem we're going to look at, question 4, it's going to be a little more interesting. I'm going to start going through these a bit quicker because I hope you've gotten the hang of the technique. So cosecant of something is equal to 7. Well, whenever I see one of these inverse trigonometric ratios, I want to turn it into a primary trigonometric ratio. So if I look at this as 1 over sine of whatever is here, whatever the argument is, I have 1 over sine x minus 1 equals 7, and I'll just rewrite this as sine pi over 2 x minus 1 equals 1 over 7, taking the reciprocal of both sides. And now we can use the same unit circle technique before. Why don't we use the unit circle with the inverse trigonometric ratios? It's just a little bit harder to visualize in my opinion. So now we're going to look at it as the y coordinate. Where's the y coordinate equal to 1 over 7? Perhaps around here. And in the first quadrant, the second quadrant, those are our arms. This is our angle alpha. You can draw the triangle if you want. And that means that our reference angle is going to be inverse sine 1/7. This side length is going to be 1/7. It is the y coordinate, the height in this case, 1/7. We have 1 as the hypotenuse. Moving on, we just need to look at how we can get to each of these terminal arms. Remember, that's also a reference angle. Well, one way to get there is just go in alpha. So our inside, our argument here is either going to be, so pi over 2 x minus 1 is either going to be equal to alpha, which is inverse sine 1/7, or it's going to be equal to pi minus alpha. Pi takes me here, I've gone too far, go back in alpha. Pi minus inverse sine 1/7. But remember, you need to add your multiples of 2 pi. It's gone a little messy here and there's not a lot of room to write, but I'll keep going. X minus 1 is equal to, I'll just divide by pi over 2 on both sides. So I have 2 over pi inverse sine 1/7, and then plus, boy, this is a little tricky, it's actually 4n. Over here we have, well, 2 minus 2 over pi inverse sine 1/7, and don't forget these multiples of 2n pi is also 4n, and that's actually still not our general solution. We want to isolate x. X is equal to 1 plus what we have here, and 3, because I add 1 to the 2, and whatever we have here. Just bring that down. I'd like to get through a few more problems. So the main idea is still the unit circle. I'm not going to look too much at isolating x at the very end, except for when we have restrictions. So question 5, we do have a restriction. We're going to solve 7 cotangent 2x equals 3. And here the restriction is x is between negative pi and pi. And in fact, it includes the endpoints. This one's a little bit tougher to solve, as you might guess, with restrictions, at least in my opinion. So once again, I'm going to rewrite this using tangent. So now I have 7, and I have 1 over tangent 2x is equal to 3. Well, I can bring 7 to the other side, and I have 1 over tangent 2x equals 3 over 7. And finally, I might say that I have tangent 2x equals 7 over 3. Good to go. I'm just going to rewrite this so we have a little bit more space. Take a look at it. And here we go. So continuing question 5, we have tangent 2x is equal to 7 over 3. Hopefully I've copied it down right. X between pi and negative pi, and including the endpoints. What do we do now? Well, we look at the argument. This is what I do. I look at the argument and I try to transform this inequality to have the argument. That way when we use the unit circle technique, we know exactly what angles are allowed. So if I multiply everything by 2, I know that the argument has to be between negative 2 pi and 2 pi. Then I bring up the unit circle, and I ask myself, well, where's the slope of the terminal arm equal to 7/3? It's somewhere around here. Doesn't need to be exact, just to help us visualize it. And of course, we need our reference angle. You might be noticing a pattern here. In this case, it's not actually unit circle for our purpose, but I'm going to say alpha is going to be inverse tangent 7/3. And then using my awesome unit circle, I'm able to visualize all the solutions between negative 2 pi and 2 pi. So 2 pi would be, we start here, we go all the way around once. Negative 2 pi, we start at the positive x-axis, we go clockwise 1 full revolution. That's negative 2 pi. So that's the area we're looking at. So our first solution is just alpha. So 2x could be alpha. I don't have a lot of room, I'll just write alpha. Our next solution, we continue, is pi plus alpha. And if we keep going, we've done 1 full revolution, we've stopped. That's the end of our boundary. We can go the other way as well. So if we go counterclockwise, well, if we go negative pi, that's actually too far, so we need to add an alpha back. Negative pi plus an alpha. If we go negative 2 pi, that's also too far. We're going to add an alpha. So negative 2 pi plus alpha. And notice that here, when we have the restriction, we're actually not going to add some arbitrary multiples of 2 pi because we already have all the solutions, right? There are a finite number of solutions when we limit the input. To solve this, we'll have x is equal to, and here I'm going to rewrite it with inverse tangent 7 over 3 to present as my final answer. 1/2 inverse tangent 7/3. Then we have pi over 2. Don't forget that's also on the right hand side. We also need to divide it by 2. Plus 1/2 inverse tangent 7/3. Here we have negative pi over 2 plus 1/2 inverse tangent 7/3. And last of all, we have negative pi plus 1/2 inverse tangent 7/3. So I hope you got a good look at that. We'll be moving on to the next question shortly. question 6, we're back to something a little more familiar. We have tangent pi x equals negative square root 3. And you might recognize negative square root 3 as something very familiar to the tangent function. You'll remember an exact value for it maybe, or perhaps just square root 3. But again, unit circle, systematic. I draw the unit circle. I ask myself, well, tangent, when is the slope equal to negative square root 3? Perhaps around here. That would get me a slope of negative square root 3, or the other way. I can draw the reference triangle again, alpha, and alpha is just going to be inverse tangent of square root 3. So to get our first solution, to get to this first bit, we're going to go pi and then minus alpha. Pi minus, well, alpha is just inverse tangent square root 3. And here I'm going to introduce this idea of different periods. For sine x, cosine x, you add arbitrary 2n pi. For tangent x, you just need to find any answer, and to get the rest of your answers, you're going to add pi n, or n pi, some multiples of pi. So n is an integer here. It might be pi, 2 pi, 3 pi, negative 17 pi, because look, if I get to the first terminal arm, I can get to any of the other solutions by going pi in either direction as many times as I like. So if I go pi counterclockwise, I've made it to the other arm. If I go pi and then another pi, I've made it. If I start here and I go pi clockwise, 1, 2, 3, 4, it doesn't matter how many times I do it. We're almost done now. We divide by pi on both sides, and we have 1 minus 1 over pi inverse tangent square root 3 plus n, because pi n divided by pi is just n, where n is an integer. Next one, we're going a little bit faster now. 7, we have 2 sine 4x equals 1. I'm going to do the same thing because this question actually has a restriction. We want x to be between 0 and pi over 2, including 0 because it's less than or equal to 0, and excluding pi over 2 since it's strictly less than pi over 2. Same idea, I want to manipulate my inequality in order to get 4x. So if I multiply by 4, I happen to get, well, 0 times 4 is still 0. If I have pi over 2 here, well, multiplied by 4, I get 2 pi. And that's our new restriction for the angle, the argument of the sine function. I'll isolate the sine function. So sine 4x equals 1/2. I'm going to draw my circle. Just a sketch. Where is the y coordinate equal to 1/2? It's equal to 1/2 maybe around here in the first quadrant or here in the second quadrant. Same idea with the reference angle. In this case, I won't need to use the inverse trigonometric functions because 1/2 is a number that we know for sine. It's a special number. How can we get to 1/2 for sine? That's just pi over 6. So I'll say alpha is pi over 6 right away, or you might do arc sine of 1/2, also getting you pi over 6. So that means that the input for x is going to be, and keep in mind the arguments between 0 and 2 pi, so I start at 0 and I can go to 2 pi, and that's everything that I can have. I can't have anything negative. I could have 0, but turns out 0 doesn't actually satisfy the equation. Our first solution is alpha, which I'll write pi over 6. The next solution is pi minus alpha, which in this case is 5 pi over 6. And if I keep going, so the arguments between 0 and 2 pi, that's my first solution. Second solution, I keep going, I've gotten to 2 pi, no more solutions, and I'm done. Now I just isolate x, divide by 4 on both sides, and I have pi over 24. Over here, I have 5 pi over 24. And I'm done. Question 8. This is going to be a general solution question. 2 cosine x minus 1 equals square root 3. I'm going to isolate the cosine function. So divide by 2 on both sides, and I have cosine of something is equal to square root 3 over 2. No restrictions, luckily, so I can just draw my unit circle and carry on. And just find the solutions and add multiples of 2 pi. So I'm going to think of cosine as the x-coordinate. Where is the x-coordinate equal to square root 3 over 2? This is a very bad sketch, but around here in the first quadrant or the fourth quadrant. Again, reference triangles and angles. Here, again, we have a special value for the cosine function. This is one that you're probably expected to remember in your courses, depending on the level you're at, of course. But we know that in order to get cosines, the value of cosine to be square root 3 over 2, we're going to need pi over 6. Happens to be the same number as last time. So to get our first solution, we might go an alpha in the counterclockwise direction. So the input here, x minus 1, undoing the cosine function, sort of, is going to be pi over 6. The other solution is 2 pi minus pi over 6, and simplifying that actually gives us 11 pi over 6. Convince yourself that's true, or perhaps you've memorized it. But this is the general solution, so in fact, this isn't quite right. I need to, don't forget this, I need to add multiples of 2 pi. 11 pi over 6 plus 2n pi. And last of all, isolate the x. So x is equal to 1 plus pi over 6 plus 2n pi, adding 1 to both sides. And similarly, adding 1 to both sides, 1 plus 11 pi over 6 plus 2n pi. This unit circle tends to be very handy for visualizing your solutions. Even if you think you can do it in your head, this is going to help you eliminate mistakes. Question 9. We are almost at the end here. We have 2 secant x minus pi over 2 is equal to 3, and we do have a restriction on this one. It's between pi over 2 and pi, written in interval notation, including pi. So x is in pi over 2 pi, which really just means x is less than or equal to pi, less than or equal to pi over 2. Same idea, I'm going to want to manipulate my inequality in order to get the argument of whatever my trigonometric function happens to be. If I subtract pi over 2, I have x minus pi over 2. And just like an equation, you subtract from everything. So pi over 2 minus pi over 2 is 0. Pi minus pi over 2 is pi over 2. So our angle, our argument, is between 0 and pi over 2, which will help us when we use the unit circle. So I'm going to isolate the secant. Secant x minus pi over 2 equals 3 over 2. But unfortunately, I don't like secant very much. So I'm going to look at this as 1 over cosine x minus pi over 2 equals 3 over 2. And then I'm going to take the reciprocal on both sides in order to isolate the cosine. So cosine x minus pi over 2 is equal to 2/3. And finally, I can use the unit circle again, just as a rough sketch, and then ask myself, where is the x-coordinate? It's cosine, so where's the x-coordinate equal to 2/3? 2/3 is pretty close to 1. Maybe it's around here in the first quadrant and the fourth quadrant. And maybe you've been noticing patterns about which quadrants the sine, cosine, tangent functions line up in when we are solving trigonometric equations. You'll find out that with the cast rule, but I like the unit circle better. Cast rule is just memorization. This makes a bit more sense. You're able to visualize it. Solving from here, this is not a general solution. We have some restrictions. We have a finite number of solutions. Again, I'm just going to carry on using my reference triangles. Here, alpha is going to be inverse cosine of 2/3. What do I do now? Well, alpha is inverse cosine 2/3. How can I get to each of these where the input is going to be between 0 and pi over 2. So the input is x minus pi over 2, the input to the cosine function. What angles will get me to 2/3, to one of these terminal arms? Just alpha. And I'll write inverse cosine 2/3. Why are there no more solutions? Because I'm only between 0 and pi over 2. This is my 0, pi over 2, pi, 3 pi over 2, and so on. Between 0 and pi over 2, this is all I'm looking at. This is maybe my search space, if you like. So that's my solution. X minus pi over 2 equals inverse cosine 2/3. And x is equal to pi over 2 plus inverse cosine 2/3. Last of all, we're going to look at a fun example. Well, I consider it fun. Maybe you don't like it. And you probably won't see this in your class because it doesn't show up very often in applications. But we have 1/4 cosecant x squared, interesting, is equal to 1/3. No restrictions, so you need to find the general solution. I'm going to multiply by 4 on both sides in order to isolate my trigonometric function. There we go. And again, I don't like to see the cosecant. I'd much rather see the sine. So 1 over sine x squared is equal to 4/3. I take the reciprocal, and I have sine x squared is equal to 3/4. Again, just carry on drawing my unit circle. I'm going to look at sine as the y-coordinate. Where's the y-coordinate equal to 3/4? Maybe around here in the first quadrant, here in the second quadrant. Draw my arms, draw my triangles, and look at my reference angle. Here, alpha is going to be inverse sine 3/4. So that means my input, in this case, whatever's inside my sine, cosine, or tangent, x squared, is going to be equal to, I could go alpha, which is just inverse sine 3/4, or I could go pi minus alpha, pi minus inverse sine 3/4, but don't forget you actually need to add multiples of 2 pi. So add 2n pi. But we're not done yet, and this is why I'm going to call this a bit of a tricky problem, because we have x squared here. We can't isolate it all the time. Like, for example, if these are negative, you don't have real values of x that'll satisfy the equation. But I'm just going to go ahead and say x is equal to plus or minus the square root of this thing, inverse sine 3/4 plus 2n pi, where n is an integer, and then square root, don't forget the plus minus, make your algebra teacher proud, pi minus inverse sine 3/4 plus 2n pi. There, I hope you can see that. Might have been cut off for some of the earlier ones, but hopefully it was still helpful. There we go. Not all values of n will actually make this work, but for the most part, this is what I'd consider a general solution to the equation 1/4 cosecant x squared equals 1/3. This brings us to the end. I hope you've enjoyed this, 30-minute session of me just going through 10 trigonometric equations in some bit of detail.